preimage size of a factorial zeros function. So for this problem, we are having a fx function to be the number of zeros at the end of factorial of x. So the factorial of x is going to be just 1 times 2 times all the numbers to x, and by convention, zeros factorial is going to be 1. So for example, f3 is going to be 0 because factorial of 3 equal to 6 and has no zeros at the end, but factorial of 11 is going to be 2 because there are 2 zeros at the end. Yeah. So giving an integer k, we're going to return the number of non-negative integers x have the property that fx equal to k. So what is the meaning? Maybe it's difficult to understand. Let me just explain it. So if k equal to 0, this means how many numbers the factorial gonna be some number and with no trailing zeros. So for example, 0 factorial, it is 1, there's no trailing zeros. Factorial of 1 equal to 1, there's no trailing zeros. What about 2, 3, 4, and 5? Yeah, let's just write that. So factorial of 2, factorial of 3, 6, factorial of 4, 24, factorial of 5, 120. So how many numbers? So from 0, 1, 2, 3, 4, there's no trailing zeros. But for factorial 5, there's a trailing zero. It is not okay. But how many numbers? In total, there are going to be 4 numbers. So we're going to return 5 because there are 5 numbers with no trailing zero. What about k equal to 5? If k equal to 5, this is something really strange. Yeah. The strange thing happens, but we don't know. If the trailing zero with 5 zeros, we cannot find any number, so it's going to be 0. What about 3? If trailing zeros is with 3 trailing zeros, we can find 5 numbers. Yeah, so definitely, for example, 2 and 3 is going to be really difficult to imagine. Yeah, it's really difficult to find such examples. But let's just try to understand the problem like this. So if we know this is a 0, right? If we know for 0 there's no trailing zero, there's 0 trailing zero, and up to number 4 the trailing zero is still 0. But for this number 5, how many trailing zeros? It is 1. What about number 6? There's 1 trailing zero because 6 factorial is 720. So what about 7? So 7 times this number, I don't know. Maybe there's only still 1 trailing zero. There's only 1 trailing zero. I don't know. Maybe after some number, maybe this is 11. Yeah, according to the example, maybe this is 11. There are 2 trailing zeros. Now, what did we say? Even for 5 trailing zeros, there's no such number, but maybe it has 4, or maybe after some number it's gonna have 6. As we can see, the trailing zeros from 0, 1, 2, 4, 6 is increasing with the number increasing. So this means maybe this is a boundary search problem, because the number of trailing zeros is dependent on how big the number is. If the number is bigger, there will be more trailing zeros. Maybe it is like this, we don't know, but definitely it is monotonic increasing. So this means we can use a boundary search to find the problem. Yeah. So the idea is that for 0, for example, if k equal to 0, definitely for boundary search we're gonna find this number. But the answer is 5. How can we get this 5? So this means if k equal to 0, we're going to use k plus 1 minus k. So k0 it is at this position, but k plus 1 it means the number with 1 trailing zero. What is going to be the smallest number? It is this is number 5, and then we're going to use this number or the index 5 minus the index 0. It's going to be 5. So this means how many numbers with no trailing zeros. Yeah, so this is just the idea. We're going to use the boundary search, and we're going to use the k plus 1 minus k. Actually, the programming is going to be really easy. Let me first write a check function. So the check function is going to be a threshold inside and a k. and I'll give a pass because I will write it later. I will first explain the boundary search part. So I'm gonna pass a k into the boundary search because I'm gonna run it 2 times. Yeah. So I'm gonna prepare L and R and result. So for L, it's gonna be starting from 0. But what about this R? It's gonna be really difficult to calculate. Yeah, because for the k, the maximum is gonna be 10 to the power of 9. This means that there's gonna be 10 to the power of 9 trillion zeros. But how can we find the number with the 10 to the power of 9 plus 1 trillion zeros? This is going to be really difficult to find. But we can use a bigger number. Maybe we're going to use a bigger number, 10 to the power of 10. Yeah, definitely there are going to be more trillion zeros. 10 to the power. So we're going to use a 10 to the power of 10. Maybe we're going to try it bigger, 10 to the power of 12. And the result is going to be 0. So while L less than equal to R. Yeah, if you think, oh, this is too small, maybe I want to try 18. Of course you can try. Let's just try 18. 10 to the power of 18. Definitely there are going to be more trillion zeros. Definitely we can find some number which is more than 10 to the power of 9 plus 1. Yeah. So here I'm going to use M. It's going to be L plus R undivided by 2. So now I'm going to use the check function. So if check M and I'm going to pass a k. I'm going to use this value k. So if this is valid, so it means I meet the condition. There's for the first example, maybe there's a 0 trillion zeros, but I want to find the smallest number. How can I find the smallest number? So R going to be M minus 1. So else, if it is not possible, so L going to be M plus 1. Finally, I'm going to return the result. So this is the boundary search part. Definitely, I want to try to find the smallest number. So finally, I'm going to run fk plus 1 minus fk. Now, we just need to finish the check function. So this is similar like giving a number. For example, this number can be 5 or some other numbers. We just need to check how many trillion zeros. If it is more than and equal to k, definitely it's going to be true. How can we find? I'm going to prepare a result. So while threshold, so threshold gonna divide it with 5, this number. Yeah, because according to the problem, if we are giving a number like 5 or 10, how many trillion zeros, we can use this kind of algorithm to solve it. We just need to check how many 5s, because there are going to be more 2s than 5. Yeah, there's going to be more number of 2s than number 5, from 1 to 5 or from 1 to 10. So the idea, because 2 times 5 equal to 10, it means it has a trillion zero. So we're going to use this kind of idea to count how many zeros. So the result going to plus equal to the threshold. So finally, the result going to more than equal to k. If it is more than or equal to k, it means valid. So we're going to make it smaller. So for example, like 0, 1, 2, 3, 4, 5. Yeah. So for example, at here, oh, we find it is okay because k equal to 0 and result is 0. So we're gonna shift until we shift to this place, and then we're gonna return the result, which is gonna be 0. Next, we're gonna try to find how many 1, and for this 5, we find how many 1. It's gonna be here. Now we're gonna use this one, 5 minus 0, which is gonna be 5 for the first example. Now let me just run it. It didn't work. Let me check. Yeah, this means I cannot pass. Yeah, let me think about it. So this is the L and R and the result. Yeah, because I didn't prepare the result. If the check function is okay, so I'm gonna prepare the result, gonna be equal to the M, gonna be equal to this number, the threshold. Yeah. Now let me just run it. Now as you can see, it works. Now let me just submit it to check if it can pass. As you can see, it passed for testing cases, although it is a little bit slow, but I think it is okay. But basically you can try 10 to the power of 10, because for this number, definitely there are going to be yeah, there's going to be a good limit if this k equal to 10 to the power of 9. This means, yeah, which number going to have 10 to the power of 9 zeros? Which number going to have 10 to the power of 9 plus 1 zeros? Yeah, we just need to find such big number. For 10 to the power of 9, maybe we don't have so many zeros. It's going to be a bigger number. Maybe we're going to try 10 to the power of 10 or 12, I don't know, but we have to try maybe. Yeah, because definitely for the calculation it's going to be really difficult. Maybe we're going to guess a number. What about 10 to the power of 10? Yeah, as you can see, 10 to the power of 10 is a better guess, and it's really fast for testing cases. Yeah, maybe for us, maybe we're going to use 10 to the power of 12. It should be big enough for us to solve this problem. Yeah, because definitely for calculating how many zeros, we can roughly use the calculation, because 10 to the power of 9, we can roughly use this kind of calculation to check how many zeros for our guess, because this is not just a random guess. We have some calculations to make it accurate. So for example, if we try to use 10 to the power of 12, we just need to check how many 5. Yeah. So 10 to the power of 12 divided by 5, it's going to be which number? Yeah, because according to this check function, definitely we can calculate. Yeah. So it's going to be 10 times 10 to the power of 11 divided by 5. So it's going to be 2 times 10 to the power of 11. Yeah. So this means we're going to have so many number of 5s. Definitely it's going to be more than 10 to the power of 9. If it is like that, so why not we just use 10 to the power of 10? Definitely it also works. So 10 to the power of 10 divided by 5. So it's going to be 2 times 10 to the power of 9. Definitely it is more than 10 to the power of 9. Even this maybe, still it is too big. Maybe we just need to use 5 times 10 to the power of 9. This might be a better guess. So divided by 5. So what's going to be the final result? So it's going to be 1 times 10 to the power of 9. So this number is big enough, because our k equal to 10 to the power of 9, and this is 10 to the power of 9. It is equal. So this means if we want to make a number which is going to be 10 to the power of 9 plus 1, which is going to be this number, 5 times this one plus 1. So this is our limit. So we're going to use this limit to guess. It means 5 times 10 to the power of 9 plus 1. So we're going to use this one. It is 5 times 10 to the power of 9 plus 5. So this is going to be our limit if we do the right calculation. Now let me just run it. Yeah, I mean, this is not a random guess. Definitely we can calculate what's going to be the better minimum value. As you can see, it passed, and it's really fast. Yeah, I think that's all about it. Thanks for watching. See you next time.